Wow, you don't need this, Mr. Abundance. You're already too cool. What do you mean? I don't get it. Don't need what? Okay. All right. Happy Friday. Week 1 of virtual learning in the new world is almost over. Never mind, you are late. I'm not late. I'm on time every day, right at 11:30. Right? I always nail it. Okay. Barely. Yeah, right. Come on. Come on. Barely. 11:30 on the dot. Absolutely. Set your clock by it. I wouldn't dare show up late. Talking about radioactive decay, radioactive growth, or exponential growth and decay. Right, sometimes radioactive decay. So, for example, Brickium-10 is a radioactive isotope. Currently, there's 113 grams of it. However, 3.4 thousand years ago, there was 160 grams of it. What is the rate of decay? Right. This is one of those examples where it can be confusing to choose the initial amount, right? Because we know two things. Currently, there's 113, and 3.4 thousand years ago, there was 160 grams. Sometimes people get confused about which one to use as your A0. Now, technically, we could do the equation either way. Now, depending on which one we choose, we'd have to make some small changes throughout it. Okay, but whenever we first talked about this problem in class on the live stream, we decided we're going to just choose the initial amount to be the earliest amount that we know. Okay, A0 will always be the earliest amount that we know. So what that is for us is 160. K, we do not know. And that makes sense because the question asks us, what is the rate of decay? Right? And the other thing I know is that it decayed from 160 down to 113 grams. So I know that if I think about starting here, so if I'm imagining starting in the past whenever there was originally 160, and then 3.4 thousand years went by. So if I plug in 3.4 to whatever the equation is, I know I would get 113 because that's how much is left today, currently. So I'll make my model. 160 e to the power of k times t. That's all we can put so far because we don't know what k is, but we're going to figure it out. And we're going to use that piece of information about knowing 3.4 thousand years go by, and now there's only 113 left. So what in the world are those? If I plugged in 3.4, I know the answer that I should get is 113 based off the information that the problem told me from the beginning. We'll do our quick solve. So we would first divide 160, take the natural log of both sides to get rid of e, and then divide both sides by 3.4. And calculate alpha y equals 1 natural log 160, and in the denominator 3.4. Negative 0.732. Oh, I didn't actually typed in the wrong piece, huh? Let me go again. So actually I put 1360. So let's get rid of that. 136. Okay, how about that? I think that's good, yeah? $160, not $136. Nice, nice, nice. We'll try it again. 160. Maybe. Okay, yeah, 113 divided by 160. Sorry, my screen went away, so I couldn't see it. 3.4. Okay, we'll try it for the third time until someone tells me what's wrong with this one. Natural log 113 divided by 160 divided by 3.4. I think so. Yeah. So negative 0.102. It makes sense that my answer is negative because we're talking about things decaying. So it should be a negative value for K. Now let's actually put this in some context. What the heck does this mean? So this means that it decays at a rate of 10.2% per 1,000 years. So it decays 10.2% every 1,000 years. I'm not seeing anything saying that I did this wrong yet. So I think it should be good. That's a big if. Big maybe. All right. So let's move on today to similar style of problem, but regarding things that are cooling down. So we'll talk about, whether it's a cup of coffee that's cooling or a pizza that you take out of the oven or a water bottle that you put in the fridge or, whatever. It will cool according to this model. And so at first glance, it looks a little more complicated than the one we're used to working with, and that's true. So you might still notice that we still have e to the power of kt here. Right, that part hasn't changed from our exponential growth formula. But now we have all this new stuff. We have this TS, we have this T0. So yeah, what does all of this stuff mean? So T0, just like how we had in our exponential growth or decay, that A0 means the initial amount. So same thing here. But instead of amount, we're talking about things cooling down. So the initial temperature, okay, whatever it is. And TS is the temperature of the surrounding environment or area. Okay, so whether that's the temperature of the room or the temperature of the fridge or the temperature of the oven or, whatever, right? These things that are cooling down are surrounded in some sort of environment where the environment is colder than it is. So that's why it's cooling. So we need to know what that temperature is as well. Okay, let's kick this off with some basic examples. A cup of coffee sits in a room that is 20 degrees Celsius. The cooling rate is 2.7% per minute, and the current temperature of the coffee is 76.3. Okay, so coffee sits in a room that is 20 degrees Celsius. So that tells me that my TS is 20. The room is the surrounding area of the coffee. It's cooling at a rate of 2.7% per minute. So negative 0.027. Again, we still have to transfer or change our percent into a decimal. And it would need to be negative since it's cooling, right? The temperature is decreasing, so we need a negative K value. And the temperature of the coffee is 76.3. So T0, 76.3 degrees Celsius. So what will the temperature be in 4 minutes? Well, first, let me just create the model. There, I'll write it down here so I have more space. So the formula, I'm just going to plug all these values into my formula first. So C of T, right? Need to look back here if we need. So the surrounding temperature goes first. So that's 20 plus T0 minus TS, so 76.3 minus 20 e to the power of k, negative 0.027 times t. And actually, before I do anything else, I'm going to go ahead and simplify this a little bit. All right, 76.3 minus 20. All right, I know it's 56.3. So if number one asks me, what will the temperature be in 4 minutes? So 4 minutes from now into the future means I will just plug in 4. So 20 plus 56.3 e negative 0.027 times 4. Right, so all that happened was we plugged in 4. Now, be careful about, sometimes people try to combine these two. I see sometimes people will add these before they start doing anything. We cannot add those together, right? Because 56.3 has this E stuck on the end of it. So these two terms are not like terms. It would be like trying to add 20 plus 56.3x. We can't do it. All right. So do not add that 20 and 56.3 together. Leave those separate. But like before, we'll go ahead and do this all in one swoop. Aiden says 70.5. I don't know, maybe. Let's calculate. 20 plus 56.3 second natural log negative 0.027 times 4. My God, he was right. Well, sort of. Again, just as a general rule, let's keep it to 3 decimal places. So 536 degrees Celsius. Again, for the calculator, make sure when you enter that exponent that you use the negative symbol, which is at the bottom of your calculator, not the minus sign. Right, so the negative symbol versus the minus sign. So you can see a difference. I mean, I know it's subtle. You can see a difference on the calculator between the two symbols. So the negative one is the one at the very bottom. Question. Hit me. Will it always be Celsius? No. This would work with any degree. It can be Celsius, Fahrenheit, Kelvin. No, it could be any unit of measurement. You know, I'm just, you know, I'm from Taiwan, so we like to use Celsius over there. I know you barbaric Americans are still always using the imperial system like Fahrenheit and feet. I just can't understand what those things even mean. You know, people tell me, "Oh, I weigh 120 pounds." I'm like, I don't know what that is. Can you transfer that to kilograms for me? Glitching, cutting out to anyone else? I hope not, because that was a really good rant about metric system and imperial. All right, let me. How's this? Same? Better? Bad? Worse? Okay. Cool. So did you not hear my rant about temperature, or did you not hear my actual answer to the real question of does this only work with Celsius? Those are two very different things. That's a shame. That was a good one. That was one for the ages. Point is, we heard them. They were just really weird. That doesn't sound like me. Okay, I'm a very normal and well-adjusted human being. So, but yeah, the point, we can use Celsius, Fahrenheit, whatever. I typically always use it in Celsius though, but it'll work for anything. All right, number 2. What was the temperature 4 minutes ago? Okay, so for number 1, we just took our model and we plugged in 4. But now for number 2, we want to plug in -4 because we're talking about going 4 minutes into the past. So we'll represent that by using a negative. But other than that, it's my same formula. 20 plus 56.3 e to the negative 0.027 times -4. And again, I will calculate 3 e to the power of and we should get 82.721 degrees Celsius. So remember the difference between asking about something, a temperature or an amount in the future versus a temperature or amount in the past. We might need to use a negative to represent whatever our value for the time is. Right, we're talking about going backwards 4 minutes ago. All right, so let's crank it up a notch. So besides that's just doing a basic calculation, right? That's just first we just had to figure out the formula, but once we knew the formula, we could just plug in whatever values because the question was easy. What's the temperature? All right, well, we plug in a number, we get the temperature. But now, let's say a cup of coffee is currently sitting at 84.9 degrees Celsius, and it's on the counter in a room that is 22 degrees Celsius. After 7 minutes, the temperature of the coffee will be 74.2 degrees Celsius. Question 1, what is the cooling rate for the coffee? All right. Let's roll through. Currently 84.9 degrees. So that's my T0. The room is 20. What? Do you guys see how straight that line, that blue line is that I just drew? Like, honestly, are you seeing this? Because it's like perfectly straight. And that's drawn using this pen. This is wild. Like, you guys are applauding in your house, right? Like, you're going to get your parents and stuff. Like, Mom, come look. Like, like, can I get some PogChamps in the chat or something? Like, this is wild. That was a great line. I'm proud of myself. Okay. Thank you, Matthew. All right, some applause. Thank you. Okay, well, you accidentally put a resident sleeper there. That was a big accident on your part. You meant to stick to the PogChamps, but that's okay. We all make mistakes. All right, so the room is 22 degrees. And after 7 minutes, the coffee will be 74.2 degrees. So whatever my formula is, I know that whenever I plug in 7 to it, my answer should be 74.2. All right, so let's just first build the model before we start actually solving anything. So TS plus T0 minus TS e the power of K times T, because I don't know what K is. So what is the rate of cooling? I'm going to use my formula. And the fact that I know whenever I plug in 7 for T, I should get 74.9. So just like last time, you'll notice that I just went ahead and simplified that. I did the subtraction to get 62.9. Now I have everything set up like I need to actually solve for K. Right. So first thing, I'm going to subtract 22 from both sides, right, which will give me 52.9. Divide by 62.9 on both sides. Take the natural log of both sides. And then divide by 7. 74.2. Oh. Okay, so 52.4. Okay, I think that's 74.2. No, not 0.4. What am I doing? So 52.2 divide 62.9, natural log of both sides, divide by 7. That good. Having a tough time today. I'm too focused on that straight line that I drew. Someone clip that. Let me calculate. Natural log, 52.9, 62.9, all over 7. No, not 52.9, 59.2. I still keep saying 9. Negative 0.027. I don't feel confident about that because I've screwed up so many times. So if you can confirm, go ahead and do so. But this is what I have. Correct. Okay, cool. Notice that rounds to 0.27 because it's 0.0266. So that second 6 bumps the third decimal place up to a 7. Right, so this is the rate of cooling, or we could say it cools at a rate of 2.7% per minute. All right, that's the actual context that tells me what this number actually means. Yeah, negative 0.027. Great if that's the right number, but what does that number mean? All right, awesome. Whenever we get back into lead 3 years from now, yeah, hang that up with the artwork. That's I'll let you guys get another quick glimpse of that before I move on. I mean, that's I can't teach that, you know. That's pure skill, raw skill. All right, so second question. Now, first off, notice this is the same problem from before. Yeah, this is the same thing. I just copied it over to the next thing. That's why we're starting with number 2 here, because this is still part of that last slide. So we already know the formula that we stated was 22 plus, what was it? 62.9 times e to the negative 0.027 times t. Right. We know this is our model from information given, and then this highlighted portion is what we just solved for in the first question, is what is the rate. Okay, so number 2, temperature of the coffee after 13 minutes. So we're just going to take our formula and we're going to plug in 13. So we do that really quick. Right, which I believe should be this. Right, so all we did was just plug in 13 for T. Number 3, what was the temperature of the coffee 2 minutes ago? So remember, the way that we represent that whenever we substitute it into our equation is with a negative 2. So I take my equation, I plug in negative 2. I believe we should get 88.390 degrees Celsius. Just the key thing to make sure you don't mess up on is, since it's talking about the past, we make sure to use that negative. Wow, that's really bad. That red in the purple highlighter. Yikes. And then question 4, how long would it take to cool to 30 degrees Celsius. All right, so whenever I have a question that says how long, I know then that I should be solving for t. I shouldn't be plugging in a number for t because I'm trying to figure out what is t in order to reach 30 degrees Celsius. That's my goal, is to figure out that much time to hit that. So let me use my formula. 22 plus 62.9 times e to the negative 0.027 t. This is what we started with at the very beginning. Well, at the very beginning of this slide, right? That's just exactly this. 22 plus 62.9 e to the negative 0.027 times t. Okay, but now I want to specifically know, when is this going to reach 30? So we solve. First, subtract 22 from both sides. So 30 minus 22 would give me 8. Divide 62.9 on both sides. So divide 62.9. Take the natural log of both sides to get rid of e. So natural log. And then divide negative 0.027. And we shall calculate. If I could find the buttons. Natural log. That should equal 76.374. And that is in, so that's a time. This problem is based on minutes. It doesn't have to be minutes. Some problems might say seconds or hours, but this one is minutes. So it takes 76.374 minutes to reach 30 degrees Celsius. Okay, so it's the same processes of solving that we used in the past 2 days of our exponential growth and decay. The only difference now is it's a slightly different equation where we have, first there's the temperature of the room or area, whatever, added in front. And then this part, instead of just being the initial amount, it's the initial amount minus the surrounding area. Okay, but other than that, same ideas, basically the same solving. We have a couple extra steps, right? Like in this one, we have to subtract 22 first. And then, great, once we do that, now we divide, natural log, divide again, etc. And we use positive and negatives to represent going forward and backward in time. But that's, yeah. That's the last thing I had. So I sent you all a homework assignment that's just, it's a little worksheet that has lots of cooling problems on it. Okay, it's talking about pizzas and ovens or cups of coffee or whatever. Okay, so work on that practice for sure. Make sure you can do it. Any questions for me? If you have a question about the notes right now, or if you have a question about the homework from a previous night, All right, we still got some time here. Typically, we go until 12:30, but didn't have a ton to do today, so I'm happy to sit here and answer questions or work through anything else that you'd like to see. Just let me know. Talk about how good of a line I drew. I'd be willing to do that. Are we going to have a performance task? Sort of, yes. It'll look a little different, but we'll still have performance tasks, yes. And we still have a while. We probably still have another week, probably at least another week until we need to worry about that. So I won't get into it too much, but we'll still have performance tasks. Yeah. Yep. Okay. Any other things? Nothing. Anything exciting, super exciting happened this week for you guys? School related or otherwise, besides all the insanity? Anything good? Any positive stories we can share with each other to keep us in a great mindset? You get to work. Where do you work? Somewhere essential. Went for a walk. Nice. Okay. Love it. Enjoy the outdoors. Hy-Vee. Oh, yeah. So you're definitely essential. All right. So you've been like secretly hiding away all the cans of soup and stuff for yourself, paper towels, toilet paper. What other dumb things have people been buying? Yes, nice. Gotta stay safe. What's a Hy-Vee on Tuesday? Monday? Wednesday? Which day was it? Wednesday, I think. Yeah. It wasn't too bad. I thought it would be crazier than it was, but it was pretty calm. And most of the stuff was, I mean, so it's definitely picked over for things like pasta or bread, I guess. I don't know. Do you guys have freezers full of bread or something? Why is everybody just buying up all their bread? I don't, but yeah, like bread, pasta, rice. I mean, but other than that, it was pretty normal. If anything, there was more stuff than usual. There's just like tons of pallets of chips and stuff. No, actually, that's not true. I was trying to get some hint of lime Tostitos, and they were completely out. Leo, do you have those in stock right now at your Hy-Vee? Do I need to go there immediately? Because that did turn this into a terrible experience for me, that there were no hint of lime Tostitos. And Tostitos, if you're watching, I would love to be sponsored by you. Just contact my agent, and we will talk about an endorsement deal. Maybe. It's okay. I went ahead and bought the Hy-Vee brand lime chips instead. I'll persevere. Nothing else? Come on, I know you guys got good stories. Okay. I guess that's that then. I'll um I'll be in office hours later. If you have some questions, please look at the homework. Try some of them out. Try all of them out, ideally. But make sure you can do the stuff. And hit me up with any questions. I don't have any streams planned for over the weekend, like office hour stuff. But I mean, I can. If a lot of people need it, let me know. If you need to ask questions, we'll figure something out. But otherwise, I hope you have a good weekend. Proud of you for making it through your first week. Proud of you for showing up and watching this right now, wherever or whenever it is. And have a great day. Stay safe. Stay healthy. See you guys.